Start recording. Full screen. Okay. All right. Good evening, everyone. As usual, my name is Sattar Shide. I am a PhD scholar at Electrical Engineering Department of IIT Bombay, and my area of work is electric machine design. So these classes are doubt clearing classes of the NPTEL course, Electrical Machines 1. There are 3 doubt clearing classes every week. This is the second one, which is arranged every Saturday, 7 to 8 p.m. There was another class today itself, 4 p.m., where Sai has discussed about windings of DC machine mostly. Here I will mostly talk about why at all DC machines are being used till date, and not being used, why DC machines are being taught. Okay. They are being used. Okay, so why they are being used and why they are not used. Okay, might sound confusing, I will explain. And some general discussion about any kind of rotating machine. Any kind of rotating machine. Some general discussion about that. Okay, so we will start in a reverse fashion. We will start from here. Why rotating machines are still used. Sorry for that. Some basic concepts about rotating machine. So any rotating machine, since this is the first class of rotating machine of this course, and this is the only rotating machine that we will study in this course. So any rotating machine has 2 parts. One part is static and the other part rotates. So the part that is static is called the stator, and the part that rotates is called the rotor. Now, both the stator and the rotor have some electromagnetic structures on them. That may be active, that may be passive. As far as DC machine is concerned, both of them are active. Okay, so stator and rotor, how they generally look, we will see. So let us try to draw the stator of one machine. Say the stator of one machine looks like this. Say something like this it looks. So the teeth, okay, let me complete the body. It is actually round, okay, although it doesn't look round in my drawing. This is round, obviously. It's round. Okay. So these things are called teeth, or singular form tooth of the stator. So this I have drawn a stator. Now you see, in this case, so in any machine, the tooth and the windings formed on this tooth, they create the poles. We will just look at later what is pole. But if you have this kind of tooth that is protruding out of the back iron, this is the back iron, or sometimes it is called yoke. Both are used. So if you see that these teeth are clearly visible protruding out of the back iron, this kind of stator is called, or this kind of structure, not stator, this kind of structure is called salient pole structure. In DC machine, we have salient pole stator. We have salient pole stator. So if you open up a DC machine, inside you will be able to see this kind of structure where you will be able to clearly distinguish the teeth like this. On the other hand, rotors can also have salient poles. say a rotor can look like this. A rotor can look like this, something like this. So this has a salient pole, but in DC machine you will see that rotor is not salient pole. Rotor is not salient pole. It has a uniform surface on it. So if you look at the DC machine rotor from outside, it looks something like this. But if you look very closely to it, you will see teeth present. But they are constructed in this way. So I am drawing the developed view. Okay, so what is developed view? Say developed views are very much used in study of any kind of electric machine. So what we do is conceptually, say this stator if you take, and conceptually if you cut it here, suppose you cut it here, so you get a cut and they lay this structure flat on the table. So something like this will be created. So this is used in the study of electric machine very commonly. So if you cut a 4-pole structure somewhere and lay it flat on the table, this kind of thing you will get. This is called a developed view. Developed view of a motor. And there are linear machines also which do not rotate, but they just say if you have a stator like this and a small, not say when we talk about linear machine, this stator does not move as usual, and since this thing does not rotate, it only moves. Sometimes it is called mover or linear, since it goes linearly, and it just runs on it. These kind of things are used in trains, bullet train and all. They are nothing but motors, linear motors. Anyway, we will not go into linear machines in this course. They are a bit more advanced compared to this. So, problems we will discuss later.
Sir,
Yeah.
so can you explain about the silent pole? Is it normal pole or something else?
It is normal pole. See, poles you can create in various ways, but salient pole means as soon as you look at the structure, you will be able to see the poles distinctly. Salient means distinct, something that can be easily identified. So here the
So
poles.
since my question is that why we call it silent pole, why we not call it normal pole?
No. See, if you talk about when you say pole in terms of magnetic field or something, that does not change. It is the same, whether it is salient pole or not, that is the same. That does not change. Salient pole is just the name of the structure. When you look at it, you can see the teeth away from each other, or in other words, where the air gap is not uniform. See, here you have large. That is why it is salient.
Okay, sir.
Yeah. And in rotor, if you see, suppose if you cut the rotor of a DC motor, they will look like this. So there are teeth, but if you look at it, it will look like a uniform surface with very small gaps in between. So if you put, say, an iron sheet on it, it will look like a uniform air gap throughout. So this is non-salient. Now there are several combinations. Say if you study induction motor later, you will see that in induction motor, both the stator and the rotor are non-salient. None of them has protruding pole. In synchronous machine, both is possible. Whereas there are some kind of machine called switch reluctance machine where both the rotor and the stator are salient pole. There are several combinations of that. Okay, now since you talked about air gap, so so from now on, I will draw only developed view. Okay, I will try to draw only developed view. That is easy to draw and easy to understand the working. So this is the stator of a DC machine. Stator of a DC machine. I have cut it and lay it flat. So these are the teeth. This is the back iron. And this is the rotor. Say I am drawing it as a sheet since the poles are not properly visible like that. So I can call it as a sheet. So the gap between the stator and the rotor is called air gap. This is always called air gap. So if you look at a motor, say if we look into this motor, let me erase this and draw it. See how well can I draw it. Say I have this stator and this is the rotor. So you see this rotor rotates here, and this is the stator which is not rotating, it is fixed. It is fixed and this is rotating. So there must be some gap in between them, otherwise they will fall, right? Otherwise this cannot rotate. So there must be some gap. So this gap is called air gap. Do you have any idea about how long is this air gap? How much gap is there? Can someone guess between these two?
0.7 electron volt.
I am talking about gap, mechanical distance. Electron volt is an unit of energy.
Oh, sorry.
Two bodies, two things made of iron. They are kept like this with some gap in between them. Otherwise, this thing cannot rotate. A simple thing. So what is the distance between them? Air gap in smaller machines are fraction of millimeter. So how many of you have performed electrical machine lab in your undergraduate or postgraduate university? Can you quickly respond? Machine lab, how many of you have attended? No one has attended machine lab, no one has ever done experiments of electric machines? Not attend. Okay, so the machines that you will find in your university machine lab, all of them are small, not more than 1 or 1.5 kilowatt, I believe. And all of them have, all of them have air gap less than 1 millimeter. So if you have a scale in front of you, just take a scale in your hand and see how much 1 millimeter is. And these machines are having air gap less than 1 millimeter, say maybe 0.5 millimeter, or say maybe 0.3 millimeter. In this way, these machines are constructed. They have such air gaps. If you talk about very large machines, say some kind of multi-megawatt machines, 1 megawatt, 5 megawatt, they have air gaps in range of centimeters, say 1 centimeter, 2 centimeter, because of there are some constructional problems. And this kind of large air gap actually creates some other kind of problems which we will not go into in this course. But what I want you to appreciate is this constructional details of DC machine or any kind of machine for that matter, that what a small air gap is created. See, there is a stator here. So this is a stator made of iron. This is another iron body inside. And this is rotating at a speed of say 1500 or maybe 3000 or maybe even more, 6000 RPM, 6000 times a minute it is rotating, means 100 times a second. This iron body is rotating and there is a gap of only half a millimeter or even less than that. They are not fouling. They are rotating like that at such a high speed. So these things I want you to think about and appreciate how these things are made. Okay, so as of now we have talked about most of the constructional details of machine. So till now what I have drawn is, I have drawn the stator. As of now I have shown the stator to be outside and the rotor to be inside. the other is also possible. Other way around is also possible, means where the rotor, the rotor will be outside and the stator will be inside. So this will be stator and this will be rotor. And this rotor will be directly coupled to a load using a belt, maybe, or maybe a load can be directly coupled to it. These kind of machines or kind of structures are called outer rotor machines. Now see, if you talk in terms of operation, how the machine work. Say you have a DC motor. In DC motor, normally what we have is we have the field winding on stator and the armature winding on the rotor. Okay, that we have conventionally. Now, if you make a DC machine the other way around, if you have the field winding on this, means the stator, if you have inside, you still have it on the stator, but you have it inside. So now it looks like this. So if it is inside, poles will be coming out of it in this way. And the rotor is here. So you see, the operation principle does not change. That is the same. Only thing is it is outside. So this kind of structures are made to easily couple the load. For example, you might have seen some electric cycles which are coming out nowadays. One electric cycle you might have seen its advertisement on YouTube. Most probably it is called Hero Electro or Hero Electro. Something like this they call it. So there, if you look at the rear wheel of the cycle, you will see the stator of the machine. There is a machine, okay, but the stator of the machine you will not be able to see. Only thing is that the outer shell you will see, and from the shell the spokes go out, and on this the rim is joint, and there are tire tubes and etc. So the rotor which is outside, this rotates, and as a result the wheel rotates. If you have an opposite arrangement where the rotor is inside, then you have to have a separate kind of arrangement to couple it to the wheel. So this kind of system is called direct drive. You need not have any intermediate arrangement to couple the motor with the load. You directly connect the load with the rotor. This kind of arrangement is called direct drive arrangement. And this is outer rotor machine. Outer rotor machines are very popular nowadays, especially people who are working on electric vehicles and all. Many of them are working with outer rotor machines. Okay. So now that being taught, we have now some idea about the parts of the machine. Now we will go into some working principles, some common working principle. Okay, this is true for any electric machine. Any electric machine, this is true. There are two criteria. See, what do we want? We want that there will be a machine, we will connect the machine to a load and it will continuously supply the load. Okay, so what we want is, we want a continuous, non-zero average actually, not instantaneous, non-zero average torque out of an electric machine. So to achieve this, we have to satisfy two criteria from that electric machine. First criteria is number of poles on stator and rotor must be same. Okay. Secondly, the relative speed between the stator and rotor, magnetic fields must be 0. So number of poles on stator and rotor must be the same, and the relative speed between the stator and rotor magnetic fields, see, not the speed between them, their magnetic fields, that must be 0. This is because, you see, the torque of an electric machine is more or less proportional to the flux of the stator times the flux of the rotor times sine delta. This delta is the angle between these two flux, stator flux and rotor flux. So if you do not have a non-zero relative speed between phi s and phi r, this sine delta keeps on varying. Sine delta keeps on varying. It keeps on varying. So if you draw sine delta, and if sine delta keeps on varying, then your torque is this sinusoid. And if you integrate a sinusoid over a complete period, you get 0. That is why the relative speed between the stator and the rotor magnetic fields must be 0. Now, in any electric machine, I said that there are two bodies. One is the stator and the other is the rotor. Now, one of them create the field. Not necessarily always, there are many variations. In induction machine itself, this does not happen. And in DC machine, this thing happens. And the other one uses this magnetic field to convert between electric field and electric energy and mechanical energy. Both can happen. So when you have a conversion of electrical energy to mechanical energy, what will you call that machine? See, as of now, I have only talked about machine. I have not told about motor or generator. Machine is a general term. Machine is a general term. So if an electric machine is converting electrical energy to mechanical energy, what will you call it? That is a motor. And if it is the other way around, it is converting mechanical energy to electrical energy, that is a generator. Generally, what happens is the same machine can do the both. It can convert electrical to mechanical, it can convert mechanical to electrical. The same machine can do the both. Most of the cases, all the machines that I know can do the both. Electrical to mechanical, mechanical to electrical, they can do. Okay. So what do we have in DC machine? In DC machine, now we forget all the outer rotor and unconventional, not unconventional, compared to undergraduate level, they are unconventional. Nowadays, they are being used very much. So, stator of a DC machine, it creates field. It creates field, magnetic field. So how does it create field? It has electromagnets on it. Okay. It has electromagnets on it. So how to create electromagnet? We will draw. I am drawing developed view. Okay. I will draw the teeth first. So this is it. Now I will draw the winding with red. So suppose say a winding comes like this. Comes like this, and it goes up. Say I have a DC supply here. Say some 230 volt DC supply here I have. Right now, can someone tell me what this pole is? Is it a north pole or south pole? As far as our convention goes.
North Pole?
You are guessing?
Yes, sir.
See, suppose you have a magnet, permanent magnet, let us say, and the flux flowing through it is like this, going out, returning, again going out, returning. So all the flux are going out here, and all the flux are coming in, going out, coming in, coming in. So in this magnet, which is the north pole, the right hand side one or the, so I will write 1, 2, okay? See, this 1 is north pole or 2 is north pole?
1 is North Pole, sir.
Why?
Because the moving of current.
Where did you get current in permanent magnet? These red lines, what are they? What did I draw?
This is flux.
Flux. Then why did you get current?
Oh, sorry.
Flux going out means north pole. Flux going out means north pole in a magnet.
Okay, sir.
Alright. So flux going out means north pole and flux coming in means south pole. So inside a magnet, flux flows from south pole to north pole. Outside a magnet, flux flows from north to south. So here what happens? Now can you say? See, this is forcing a current like this. So right hand thumb rule says the flux is going up. So this is a south pole. This is a south pole. So if you have a south pole here, now what I will do is I will complete the drawing. So if you have a south pole here, you must have a north pole here, right? Otherwise, see what this flux will want. This flux will want to go up and go like this. It has to come out. Half of it will go this way, half of it will go that way, and it will come from here. Remember, I am drawing the developed view. I made a cut here. In reality, they are joined mechanically, right? So the half of the flux comes out and comes in from here. So if this flux goes out from here, it has to come, goes like this, it has to come out of it like this. So we must have a north pole here. So the current should be in what fashion? It should be the opposite. So the winding should be in this fashion. Is it working? No, it is. Just a minute. Should be the other way around. Oh. Just a minute, what happened? Yeah. So we have to have a north pole here. So it should go like this, is it? Yeah. Again, it will go to this winding, this thing, and again it will create another pole. So basically we have a north pole, sorry, south pole here, north pole here, south pole here, north pole here. So how is the flux flowing? See, a flux comes in. Say I am calling this flux as phi. This flux phi comes in. It gets divided. Phi by 2 goes here. Phi by 2 goes here. Right? So phi by 2 comes from this side. Another 5 by 2 is coming from this side. So another 5 is going. Again, 5 by 2 came out here, 5 by 2 came out here. So total of 5 was flowing. So you see all the teeth are carrying the same flux, right? Once they come out of the teeth, they get divided. Again, going in the teeth, they join in another branch of flux that coming from another pole. So this is the way the stator of the DC machine is owned and the poles are created. Now, can you tell me the number of poles of this DC machine? From this diagram, can you tell me the number of poles of the DC machine?
4 poles, sir.
4 poles. So south, north, there are 4 poles.
Yes,
So this is a 4-pole DC machine, or sometimes people say 2-pole pair. 2-pole pair machine, whatever. We can have any even number of poles on a machine. We can have 2-pole, 4-pole, 6-pole, 8-pole, 10, 12, 14, everything is possible. For any kind of machine, not only DC machine, induction machine also you can have 20-pole induction machine. Whatever. So this is the concept of pole. This is how the pole is created on the stator of a DC machine by electromagnets. Instead of electromagnets, it is also possible to have permanent magnets. Say if you have a DC machine stator like this, and inside if you embed some permanent magnets in this fashion. So this is one permanent magnet whose magnetization direction is this, means this is north pole, this is south pole. Another permanent magnet, opposite direction, another permanent magnet, same direction, another one, just to complete the diagram, opposite direction. So this is also possible. This is PMDC, permanent magnet DC. And this is a normal DC machine. Now, can you tell me the difference between a normal DC machine and PMDC machine? From operational point of view, there will be no difference. But there is something that we lose if we go for a permanent magnet DC machine. Can you tell me what it is? Something that we are losing if we go for permanent magnets instead of electromagnets. What we are losing is control. Control on field. So the flux that these poles create, that create the field flux, that create the magnetic field inside the machine. So instead of having, so if I have electromagnets here, I can control the current through them by using some external circuit, and hence I can weaken the field if required. But in PMDC that is not possible, and there are other problems also with permanent magnets that we will not discuss here. But just remember one thing, that permanent magnet machines are very much popular nowadays. All the electric vehicles, most of the electric vehicles, more than 90%, 95% electric vehicles that you see on road, even the e-rickshaws and all of them are using permanent magnet machines. But they are not DC machine, they are other kind of machines. Okay. Now, if you have 4 poles on the stator, you must have 4 poles on the rotor also. That we have already seen. Now, how the rotor pole is realized, that we will see. Before that, let me draw a, say, stator. Suppose this is one pole of the stator. Okay, this is one pole of the stator. We are looking it from this way, and this is another pole. This is another pole which is placed this way. Okay, let us just talk about 2. Just talk about 2 poles. Say this is north pole and say this is south pole. Right, now we have a winding, a coil. Let me draw it, sorry. Coil goes like this and comes back. we have a coil, and this is the coil axis. Do I have a, okay. Okay, so let us take this diagram. We were just trying to use this diagram. So this we have. Now you see, you have to be very careful here about the cause and effect. From now on, wherever you are studying machine, you have to understand the cause and effect to understand the difference between motoring and generating action. So you see here, the question is which way the coil would try to rotate. It has been given a current. It has been given a current through it. And since the current is flowing in the magnetic field, the coil will try to rotate. So can someone tell me whether it is a motoring action or a generating action?
Sir, motoring action because of pole.
So generator, there is no pole. Without electric field, I just discussed here that they use the field to create both kind of generation. Electric,
Electrical
mechanical,
to mechanical and mechanical to electrical.
yes, both kind of they do. Then others would like to comment. See, a motoring action means when the energy conversion is from electrical to mechanical. Here, electrical energy is given from outside, some current is flowing, and that creates a rotation. Rotation means mechanical. So this is a motoring action. Okay. Now, suppose we will come back to this. Okay. Now, suppose you have a magnetic field B, somewhere a magnetic field B, and there is a charged particle Q, say positively charged particle Q, that is moving. When a charged particle Q moves through a magnetic field B with a velocity of V, some force is experienced by the particle. Can you tell me what is the expression for that force? This is class 12 physics question. Does this equation look familiar? F equals Q to V cross B. This is just one component of Lorentz force. Lorentz force has another component, which is the simply electric field into Q. But we are not interested about electric field because electric machine there is no electric field. So as far as the air gap is concerned, okay, inside the conductors of waste there is electric field. So this is Lorentz force. Now, if you look at, so I'll take this red. So current is flowing means there is a charged particle here, right? A charged particle inside the conductor which is moving in this direction, in the direction of current. So the velocity vector is pointed is in this fashion, and the B vector is pointed in this fashion, in this direction, north to south. They are perpendicular to each other. Now can you tell me in which direction will this side of this conductor, this is say side 1, this is say side 2, in which direction will this side of conductor experience a force, upward or downward? It can have any kind of, it can have upward force, downward force, it can have force outside in this direction, it can have force on that direction. In what direction will this conductor experience a force? Can you say from this equation? See, whatever force this particle, this charged particle experience, the same force is experienced, not the same force, all the charged particle, whatever they are experiencing, the total is experienced by the conductor. So in what direction will this conductor experience a force because of this Lorentz force? Can you tell me? Using this equation, Lorentz force equation. I hope you did not forget right hand thumb rule. Now can you say? See, without this electric machine, reading electric machine is pointless. Point your these four fingers along the velocity vector, then curl them across the B vector. Then wherever your thumb points, that is the direction of resultant, the force.
Sir, upward direction?
You apply right hand thumb rule.
Oh, sorry, left.
Vidya, can you please respond? Vidya Vag. Vidya Akanksha. Vidya Akanksha, can you hear me? I don't know what you are doing. Anyway, so this will experience a force downward, F. This is nothing but Fleming's left hand rule. Same thing. There are several things to confuse the students. Left hand rule for this, right hand rule for that. All of them are nothing but vector cross product. If you look very closely, see, this is Fleming's left hand rule, right? Now you take your middle finger as the first vector, this finger as the second vector. Now apply right hand thumb rule here. See, this is Fleming's left hand rule is nothing but vector cross product. So that is the same thing we're applying. So this conductor will experience, I will clean up this garbage here. This side of the coil or this conductor will experience a force downward. Now another particle, positively charged particle, which is here, which is also moving in this direction, V. And the B is here. I will do it myself, no point of asking. So again here, the force is upward. So you see, this conductor is experiencing a force downward and this conductor is experiencing a force upward. So if we have a coil axis, like this, can you tell me, looking from this perspective, in what direction will the coil rotate? Clockwise or anti-clockwise? Looking from this perspective, this is going up, this is going down. Something like this. Clockwise or anti-clockwise? This is a clock. The hand is rotated in this direction. So this is anti-clockwise. Anti-clockwise. In this direction it is rotating. It's anti-clockwise. Okay. So since we have talked about motoring action, we will quickly look at the other generating action also. Now read the question first. If the coil is rotating in the direction specified with green arrows, then at the instant depicted in the figure, which among the following will be true? They have asked in what direction will the EMF be induced. Now you see here the rotation is given. we are again coming to the cause effect. Here the rotation is given, the mechanical thing is given. Sorry. The mechanical thing is given, and that is creating some electrical effect. So this is a generating action. This is a generating action. So let us now try to understand what will happen here. So see, now there is no current flowing in them, right? I have a field, I have a coil, I have started it rotating. Now what will happen? So there was a positively charged particle sitting here. It was sitting here. Obviously they don't stay there, stand still, but as we know that their random motions are so random that on an average the net velocity is 0. So we can assume that one positively charged particle is sitting here. It was peacefully sitting. Now what we have done is, from outside we have started rotating this coil. So now this particle sees, what does it see? It sees that it is going up. It has got a velocity of v in this direction. And there was a magnetic field B present here already. So again we will apply F equals Q into V cross B. So it was sitting here. It is moving up. Why is it moving up? Because the conductor in which the particle was sitting is moving up. So it is also moving up with the conductor. And it is moving in a field B. So there will be a force on this particle. So can you tell me in which direction will the particle try to move? Will it move away from us or will it come towards us? Will it move away from us or will it come towards us? Again, you apply right hand thumb rule. Ranjit is saying towards us. Right hand you apply, right hand upwards, V is upward. So right hand upward, curling toward your right. It is moving away from us. Or am I doing a mistake? V up, B this side. No, it is moving away from us. The positively charged particle is moving away from us. Isn't it? Again, let us take another positively charged particle here. So it was also sitting here peacefully. Now we have forced it down, going down. And the B was already present. So this is moving towards us. F. So all the positively charged particles in this, say in this BC sector, in this coil, can you see? We draw it with blue. In this half of the coil, BC sector, they will move away from us. And all the positively charged particle in DE sector, they will come towards us. What about a positively charged particle here? Just on the axis. So it is rotating across the axis. So this positively charged particle is not at all getting any motion. What about this? A charged particle here. It is going up. It has a V in this direction. It sees a B in this direction. So V cross B. It will try to go away from us. But you see, a charged particle cannot leave its conductor. This charged particle will get a force that is forcing it out of the conductor, but it cannot go. So it will not go in this direction, it will simply stay here. It will apply some force on it, but it will stay here. So basically, all the conductors present in the CD sector, they are not experiencing any force. They are not experiencing any force. Right? So now what will happen? We will clear up all the garbage and write down our observations. So,
Sir, reason behind that in CD no force moving.
okay, tell me, this particle, in which direction was it getting the force?
Is what is away from.
Away from us. So if you have a conductor here and this force is forcing this particle to go away, go out of the conductor. It cannot go out of the conductor, right? So basically this is interesting. So if you see, there will be an accumulation of positively charged particle in this region, and there will be accumulation of positively charged particle in this region. So if it is possible at all to measure the voltage on the two sides of this conductor, you will get some voltage. This is called Hall effect. It is called Hall effect. There will be some voltage, but this voltage will not let the particles move along the conductor because the force is perpendicular to the conductor. So this will not participate in the generating action. So the charged particle here that was going in this direction, charged particle here that was going in this direction. So basically in this loop we will have a current like this, right? Sorry, I gave arrow in the same direction. We will have a current like this. Now this current is flowing here. I will draw only arrows. So this is the current, this is the current, this is the current. I hope the arrows are you can understand the arrows. This is the current. So if we connect a resistor here like this, we will get the current. Right? Now can you tell me that, now see, this is now a DC generator, right? A DC generator. So say this is a DC generator. This whole thing I am drawing inside a block. A DC generator. It has a positive lead and a negative lead. Positive lead means what? If I connect a resistance, current will flow from positive lead to negative lead. Right? So here, what should be positive? Should I mark A as positive or should I mark F as positive?
Sir, F is positive because the source comes from. Yes, sir.
See, this is same as magnet. In magnet, I told you, outside the magnet, flux flows from north to south. Inside the magnet, it is from south to north. Same is the case for a battery also. For a battery, outside the battery, current flows from positive terminal to negative terminal. Inside the battery, current flows from negative terminal to positive terminal. Here also you see this DC generator is nothing but a battery. It is generating some power, some energy, electrical energy. So see, inside the coil, the current is from negative to positive. Outside the battery, it is from positive to negative. Clear? So you see, this cause effect is very much important. Whenever you are asked to find out the direction of motion or maybe the direction of current, you have to find out, you have to first see what is given to you, what is the cause. Then you have to see what is the reason out of it. Okay? So, why I told all this, now we have seen as a gist is, this is a positively charged, not positive, the positive terminal. This is a negative terminal. And the resistance is a load. The resistance is a load that can be anything, that can be a bulb. But the thing is, the machine is rotating. The machine, not the machine, the coil is rotating. And the load is directly connected to the coil in this fashion. So if this thing rotate, I have to allow this resistance also to rotate, or else all the wires will get tangled here. Can you understand the problem? Can you understand the problem? If I let it rotate and do not let this resistance rotate with it, and the coil is alone rotating, then all the wires will get jumbled up here. They might short circuit even if there is no insulation. But have you ever seen a bulb rotating with the generator? Obviously, the bulb will not rotate with a generator. So there must be some slipping contact. Slipping contact means there must be something connected at the end of the winding. Say one winding comes, connected at the end of the winding, which is rotating with the winding. And there is something other that is placed here outside, which is not rotating. So when the winding or the coil, when it rotates, this thing also rotates, and they touch each other, and electrical energy flows through the contact. Any electrical machine, if you have electrical power supply to the rotating part, you must have some contact like this. In case of DC machine, this is called a brush. This is called a brush. This brush is made up of graphite. Why graphite? Because it is a sliding contact. Things are fouling against each other, so I cannot put iron. There will be a lot of friction, lot of energy loss, lot of sound. So I have to keep something that is soft and at the same time electrically conducting, a good conductor. So something that is soft at the same time conducting is graphite. So this brush is made up of graphite, and this part for an electric machine, so for a DC machine, is called commutator. It commutates. So in general or as a combination, they are sometimes called commutator brush gear arrangement. This helps a proper supply of DC power outside. We will see how. Okay. This is the last topic we will cover now. So see, what we saw here, forget this load for now, okay. So when this conductor was here, it was creating a flow of positively charged particle away from us, and this was creating towards us. Now this is rotating. This is rotating. After some time, this DE will come here, right? And this BC will come here. Now, if I keep this end of this load connected to DE, and I keep this end of the load connected to BC, they will get twisted. That is another thing, forget about it. But you see, once DE comes here, now this DE segment will now carry current in this direction. In this direction. Because all it understands is the motion and the field. So basically, if I have a connection like this, what I will have here is a alternating current. So when DE is here, I will have a positive current. When DE is here, I will have current on the other direction. Is it clear? When BC was here, I had a current in this direction. When BC goes the other side, BC conducts current on the other way. So the current becomes opposite. But this is a DC generator. I cannot have an AC current out of a DC generator. So what is the solution to the problem? The solution to the problem is, see, whenever any conductor is there in front of this north pole, that is carrying a current away from us. And whenever there is a conductor in front of south pole, that is carrying a current towards us. Right? So, can we not do it this way? That, oh, and one more thing is when BC comes here in between the poles, it is not carrying any current. It is not carrying any current. You can find it out. Because the velocity and the field, they become parallel to each other. So it is not carrying any current. So can I not put the brushes here? So I will draw it once again here. So if I have the north pole here and the south pole here, we saw that all the conductors were carrying current away from us, and all the conductors here were carrying current towards us. And the more they move, say I am now drawing even more conductors, right? So the area of the conductor is not changing, but the current through them is changing as they move away from the field, because the field intensity is now reducing. So I have large current, the maximum current here, it is reducing, no current. Again reducing, no current. Again, no current, more, very much large, very large current. Again reducing. So this is the current distribution that we have inside the armature of a DC machine. And the conductors present here are not carrying any current. Now, if I have a brush here, obviously the brushes are not touching the conductors, but for the time being, let us say, if I have brush here, and I collect electrical energy from here, you see, I will always have current of given or constant polarity. So what will it be? That depends on which is connected here, which is connected here. So let us say it is connected here and this is connected here. So we will have current going out and coming in. So this solves our problem. So the conductors, when they are taken out, they are connected to rings like this. So let me try to draw a ring, a metallic ring like this. One ring here and another ring here, another ring here. The conductors are one is connected here, other is connected here, and on the ring there are brushes. These brushes collect energy from it and gives to the outer supply. This ring is nothing but the commutator. This ring is not commutator, this is one segment of the commutator. How many segments will be there? That will depend on how many coils are there. So what is done is, I will create some space. I will be able to cover this. Siva will cover this problem next Tuesday. So make sure you attend his class. Since we talked more about fundamentals of DC machine. So how it looks is, if you look at a commutator, it is like a cylinder. It is like a cylinder. A cylinder, and there are a lot of commutator segments on it. Commutator segments on it. Windings come and they get soldered or connected here. And at the end of the commutator, another a bit more larger cylinder is connected, and the commutator segments are continued. This is called the riser. Riser. The whole thing is commutator, and the brushes are placed here. Brushes are placed here. So you see here, where I placed the brushes. I placed the brushes between the pole. So brushes are always placed in interpolar region. Brushes are always placed in interpolar region. Interpolar region. So if you have two-pole machine, you have two brushes. If you have, say, four-pole machine means north, south, sorry. You have brushes here, one brush here, one brush here, one brush here, one brush here. So why did I discuss all these properties and everything? I will come back here. I told you that this is how we create poles on a DC machine, 4 poles, salient poles on the stator of a DC machine. But how to create poles on the armature? There we don't have salient pole, we have windings, distributed windings. There we create poles like this. We connect the windings in the commutator, put brushes at proper places, and this way we create poles on the armature. Once we have brushes, say if this is positive, this is negative, this is positive, this is negative. So this is one pole pair, this plus minus supply comes from one pole pair, this comes from another pole pair. This is how poles are created on the armature in DC machine by putting brushes at proper places. So any doubt out of it? Or else I will stop this session.
No, sir, no doubt.
Okay, you make sure that you go through this commutator concept once again. You try to appreciate why this commutator is at all required. If there is no commutator, the current will keep on changing. Once you have a commutator, then the current will be a DC current. Okay, that's all about it for today. We will meet next Saturday again 7 p.m. Thank you.
Thank you, sir.